This is the cosmic microwave background map as observed by the Planck satellite, a snapshot of the universe at what's called the time of decoupling, when the universe first became transparent to light. While it looks fairly chaotic at first glance, this image actually only maps the perturbations or fluctuations of the actual background, which on an absolute temperature scale would look somewhat like this. The cosmic microwave background thus actually displays a remarkable uniformity. A constant background of 2.73 Kelvin, disturbed only by perturbations 5 orders of magnitude smaller. In other words, the universe at time of decoupling had a homogeneous temperature across scales of billions of light years, disturbed only by tiny perturbations. And that leads to some problems. I'm Simon, and this is your 5-minute introduction to cosmological inflation. Generally speaking, there is no reason to assume that two disconnected regions of the early universe should share any similarities, and definitely not to this level of fine-tuning. Of course, if the regions had some way to exchange information, and by extension energy, there could have been a homogenizing process leading to a more even distribution. The upper limit for any such process is of course the speed of light, and we call the distance of a signal traveling at the speed of light the causal horizon. In a flat expanding universe, the causal horizon for a signal emitted at time t1 and received at a time t2 is described by this expression, which we can extract directly from the metric. The size of the observable universe today is in good approximation given by the Hubble radius, the inverse of the Hubble constant. Thus, for the case of the cosmic microwave background, which is an image observed at decoupling, the maximum size of a causally connected region is given by the causal horizon between the Big Bang and decoupling. Unfortunately, if we plug in the evolution of the scale parameter during radiation domination, we find that the causal horizon is orders of magnitude smaller than the size of the observable universe. This is called the horizon problem. A universe should consist of a huge number of independent regions between which we'd expect at least some differences, yet it appears almost completely homogeneous. In addition, by analyzing the perturbations that we can observe, we see correlations over scales that far exceed the maximum distance that we'd expect causality to impose upon us. So, how can we solve this issue? If we look again at the definitions of the causal horizon and the Hubble radius, we can connect our problem to a more general mathematical statement. As long as the expansion of the universe is decelerated, then the causal horizon will grow slower than the Hubble radius. In other words, once two regions are causally disconnected, they can never come into contact again. In that case, one way of addressing that problem is obvious. If we propose an initial phase of accelerated expansion, that could stretch causally connected regions so far beyond the Hubble scale that the entire observable universe remains within that range to this day. This period is called inflation. As a quick aside, apart from the horizon problem, inflation also solves two other problems, which are the curvature problem, the question of why the spatial curvature is nearly vanishing today, and the monopole problem, which deals with the question of what happens to topological defects that should have been generated in the early universe. In both cases, the answer is the same. A rapid period of inflation dilutes these primordial densities to the point where they're no longer observable today. To understand the implications of accelerated expansion, we take a look at two fundamental equations, the Friedmann equation and the relativistic energy conservation equation, which both follow from the Einstein equations of general relativity. Combining these equations lets us realize that to achieve accelerated expansion, the species filling the universe at that time must have a negative pressure. Clearly, this can't be explained by any matter or radiation species, but it's not impossible. For example, the dark energy that dominates the universe today has such an equation of state. The simplest approach is proposing a so-called inflaton, a new scalar field, usually denoted phi, subject to some potential v, that fulfills the equation of state. Recalling the Klein-Gordon equation from quantum physics, we can derive these central equations. We see that, if the field has no kinetic energy, h remains constant throughout an everlasting inflation. This exponential inflation is called de Sitter inflation. To obtain a long but finite period of inflation, we choose to deviate only slightly for that template by imposing that phi dot is small for an extended period of time. This model is referred to as slow roll inflation. The field is slowly rolling down the potential, allowing for an extended period of inflation. These conditions can also be expressed using the two slow roll parameters epsilon and eta, which have to be small in order for slow roll to be fulfilled. As a side note, some literature defines them in slightly different ways, but they usually express the same concept still. The duration of inflation is usually expressed in e-folds, which parameterize the growth of the scale factor in power of Euler's number. We find that, to solve the outstanding problems mentioned earlier, we need the scale parameter to grow roughly as much during inflation as it does after inflation, which corresponds to an e-fold number of roughly 70, sometimes less in the context of specific models. Finally, the end of inflation occurs when phi dot squared much less than b is no longer fulfilled, which means that the kinetic energy of the field becomes relevant compared to the potential. This is where a process named reheating occurs. The field, oscillating around the potential minimum, will decay into the elementary fermions and bosons that make up the universe today, which marks the end of inflation and the beginning of radiation domination.